Okay, so hello everyone. Welcome to the fifth interval probability seminar meeting of the semester. Today, Sasha Sodin will be speaking about a random operator constructed from the representations of the symmetric group. So take it away.
Okay, so thank you very much. It's a pleasure to give a talk here. This is joint work with Ohad Feldheim. And my goal is to indeed advertise a random operator constructed from the representations of the symmetric group, but I'll start from the end, which is the 15 puzzle. I believe all of you know what is the 15 puzzle, but let me just to make sure that we're on the same page. So does everyone know what this is? It says 4x4 square. The small squares are labeled with numbers from 1 to 15. One of the squares is empty. So where a legal move is to take one of the squares adjacent to the empty square and to move it there. It's a sliding puzzle from the 19th century, and the goal is to order the numbers from 1 to 15. So these three are colored orange, in orange, since they're in the right place. Is this okay? Any questions on this? Okay, so what we are going to do is play the puzzle on an infinite board, and will allow the dimension to be 2 or higher. That's there's no problem doing it in infinite dimensions, and the moves will be random. So we, at every step, we pick one of the 4 squares adjacent, or 2D squares adjacent to the empty one, and we move this onto the empty square at random. In other words, we get a process driven by the usual d-dimensional random walk. So let's denote by Pn of Zd the probability that after n steps we return to the original configuration. And if you don't mind, I'll also consider a measure rho on the interval -1, 1, which has these numbers as its moments. Is the setting clear? If you prefer more scientific, language than the colloquial one I'm using, then this is the semi-direct product of the symmetric group acting on ZD and ZD, and where we have the natural Cayley graph, and we're interested in the return probability to 0, and we'll raise the corresponding spectral measure. I'm not going to use it at the moment. So now,
Sasha, just to clarify, so we should think of, we have ZD and you're just doing interchanges on all, so you start with some labeling of every vertex.
Yes.
You just randomly are interchanging according to some, exponential rate times or something like that, or
discrete time.
But how do you decide where, if it's an infinite board, how do you decide where you're going to?
No. I have an empty square. It has 2D neighbors. I pick one of them at random, and I interchange.
Okay, so you start with an empty square at the origin, say.
Yes. I start with an empty square somewhere at the origin, for example. So it's driven by the usual random walk. It lives on this semi-direct product, but it's driven by the usual d-dimensional random walk.
Okay.
So now the main theorem has 2 parts which are equivalent to one another. One is so it's easy to see that these PNs are 0 if n is odd. So we'll only focus on the even ones, and we have a 2-sided upper bound. the lower bound is the same up to a log. And the second part is a bound on the tails of the measure rho. Rho of 1 minus epsilon 1 is bound from above by e to the minus epsilon to the minus d over 2, and from below by the same thing again up to a log. So it's easy to see that these two parts are equivalent to one another. My original interest in this problem came from the second part, and this is the story which I will try to tell. This looks very similar to something called Lifshitz tails for the Anderson model. I'll try to explain what it is, and I will try to explain why this thing, which has no apparent randomness in it except for the randomness of the walk, why is it somehow similar to the Anderson model. However, the first part is also of some interest in the context of random walks and groups, and I will comment on that too. Is the statement okay? So what I'll do now, I'll try to describe briefly what is the Anderson model and what are the Lifshitz tails, and then you'll see the similarity to this relation. So the Anderson model, I'll focus on the very simple, the simplest case of the Anderson model, where in dimension d, which can be now 1, 2, 3, or any other natural number, and we fix a random Bernoulli field. To each side we associate a random plus minus 1, plus with probability 1/2 and minus with probability 1/2. Independently with probability 1/2. So to each realization of this field, we associate a random operator, an operator acting on the lattice, which acts as follows. Well, I have a cosmetic factor 1 over 2d plus 1 times, it has no importance whatsoever, and we multiply it by a sum of two terms. One is something like the discrete Laplacian, the sum over nearest neighbors of x, of psi of x, and the second is a multiplication operator by our potential, by random potential. So this is a special case of what is known as the Anderson model. There are many interesting questions pertaining to the spectral type of this creature and so forth. I'm not going to discuss any of them. I'll focus on what I'll focus on is one particular question, which is also quite classical. How is the spectrum of this distributed? So it's not hard to prove that the spectrum
just all the x's in the sum should be y's, right?
Oh, y's, yes. Thanks. Yeah, it's yes, the sum of the neighbors. So it's not hard to prove that the spectrum of this operator is a deterministic set, in this case -1, 1. And now we want to know where in the interval -1, 1 there is more spectrum and where there is less. So the way to measure it involves a measure which is called the integrated density of states. It's defined as follows. It's a measure rho. I'll put a subscript and to distinguish it from the previous one. The measure of the interval AB is constructed as follows. We look at our operator and we restrict it to a finite box of size 12 plus 1. So then we get a finite matrix of dimension 12 plus 1 to the power d, right? Then we can count how many of its eigenvalues fall into our interval AB. We count how many of these are there, and we divide by the total number of eigenvalues, which is the size of this matrix, and then we take the limit as L goes to infinity. So it's the natural way to measure where do we have more spectrum, and where how is the spectrum, how are the eigenvalues in finite volume distributed. It's also equal. It's also known to be equal to the expectation of the spectral measure, let's say, associated with the vector delta function at 0. You have a random spectral measure. The measure is random, but if you average it over the realization, you get the same deterministic quantity. So this is an almost sure limit. I get the same deterministic measure, rho. Okay, and then so is the definition okay?
Can I ask a question?
Sure.
For your studies, you don't care about putting any coupling constant on the potential, or also what the Bernoulli probability is?
I assume there are plus minus ones. I trivialized it to the maximum just to make it as easy as possible. It's of course you can do it for any random variables and to put a coupling constant. But I wrote the simplest formula which illustrates my point. The point which I made.
You will not care about the transition.
I don't care about the spectral type. No, it's a very interesting question, but it doesn't have any. It's not what I want to illustrate to speak about. No. So then there is a fact which is called a quantum Lifshitz tail. Lifshitz is Ilya Lifshitz, the theoretical physicist, which says that rho the measure, the tails of this measure. So this measure is its support is always the spectrum, the interval -1, 1. But now the question is how do the tails behave? And it turns out that the tail has a bound of the same form as we saw. So let me just remind you that this. Okay, I can't fit it on one screen, but it looks very. So this is the here on top. We see this is our result for the measure corresponding to the 15 puzzle, and this is the Lifshitz tail. You see that it's looks very similar. And in my narrative, this is supposed to justify the analogy between the Anderson model and the random operators, which I'll try to define. So if that's okay, let me tell you the idea of the proof. At least very briefly. So the idea of the proof of this fact of this fact. So the first rigorous proof, perhaps in a slightly weaker form, appeared in the paper of Barry Simon, 83, and it combines a very convincing physical argument of Lifshitz with a method, an argument due to Hermann Weyl called Dirichlet-Neumann bracketing. The idea is as follows. We take our large box of size L by L, or 2L plus L by 1 by 2L plus 1, and we divide it into small boxes of size. And it turns out that there's an important characteristic scale, which is 1 over square root of epsilon. So the volume, volume of each box is epsilon to the minus d over 2, right? Since the side length is epsilon, and this is what will appear in the exponent. So now what is the bracketing? The bracketing is a way to squeeze our operator between two operators. I'll call them HV minus and HV plus, both of which are direct sums of matrices living in the blocks. So both of them decouple into direct sums over blocks. This is standard. I'm going to elaborate on this. Then how does the lower bound, for example, appear? so we look at this definition of the density of states. Well, there is a certain probability that all the potential in our box will be +1 and not -1. This is an event of exponentially small probability, but it does happen. So at least with the probability which is exponentially small in the volume, all the v's are +1s, and then by direct computation one can see that if all the v's are +1, then you do get an eigenvalue in this range, which is greater than 1 minus epsilon. So this is greater or equal, maybe perhaps to some trivial factor to the probability that a block is filled with pluses. Yeah, and this is exponential in the volume of the block. Okay, so I mean, when everything is plus, this is an easy computation. It's a shifted Laplacian, so it's very easy to compute all the eigenvalues. You compute them, and you see that there is one exactly for this choice of the block size. You see that there is one. Each of the blocks for which the potential is identically plus, you do get an eigenvalue in the range which we are asking for, and this gives us the lower bound.
Sasha, just to clarify, so the HV minus and the HV plus, this is that you set the environment to be all minuses on every block?
No. HV minus and HV plus are very similar to H, except that we play with boundary conditions in such a way. They differ from H only in boundary conditions. You can ignore, you can think that they're equal to the restriction of H to one block, except that this is not correct. H is not bounded from above by the sum of its restriction to finite blocks. But if you play with boundary conditions carefully, then so it's these are still random operators, and that's why we can do this manipulation.
Okay.
And the same from the. So in a similar way, I mean, it's a slightly more complicated fact, and you need to use the uncertainty principle in some simple form. So the idea is that if a block is not filled, okay, it's not true that if a block is not filled with ones, with pluses, then it doesn't contribute an eigenvalue. But indeed, to contribute an eigenvalue, a block has to be mostly filled. Let's say 3/4 of the signs should be pluses. And the reason is that what our operator is the sum of two terms, the Laplacian and the multiplication operator. We somehow try to make both of them close to the maximum, and if the Laplacian is so close to the edge, it means that our function is very localized in spectral domain, so it somehow has to be delocalized in the usual domain. And so we also there's a similar upper bound. Block is mostly filled with pluses, and this is still has the same bound with a different constant. Okay, so I mean, I was brief here, but the reason why I am explain this is that what I'm trying to emphasize is that these tails capture some kind of large deviation behavior of the potential, and yeah, so this is the mechanism how these tails work, and I believe there should be a proof of our theorem along the same lines, and definitely it represents large deviations of something with respect to the Plancherel measure, and I'll try to explain what the something is, except that I don't know such proof, and therefore we went along a different route which passes through random walk on the 15 puzzle. Any questions?
So can you use your proof also for the Anderson model?
Yeah, I will comment on it in a second. Yes, it won't be. Yeah, I can, and it was done essentially. yeah, it's much simpler. The Anderson model is much simpler. Somehow the non-commutativity is what makes our problem interesting. Let me explain this point. I do want to let me make a short digression to group theory. So there is a nice group. I think it was introduced. At least the name was introduced by Kamenovich and Vershek. It's called the Lamplighter group. So it's the Reth product of a cyclic group of size 2 and ZD, which is the cyclic group raised to the power ZD, semi-direct product with ZD. So in simple words, what is this? We have our d-dimensional lattice. On each vertex of the lattice, we have a lamp. Some of the lamps are on, some other lamps are off. Okay, we have a configuration of lamps. Each lamp is either on or off. Then now, somewhere on the lattice, we have a gentleman, a lamplighter, which is allowed to do one of the following two things. Either he moves to one of the adjacent points on the lattice, or he switches the state of the lamp at which he stands. Okay, so in this case, he has 2d+1 possibilities. What to do on each step. Then you get a graph. Then you get a graph of the possible moves, which is the Cayley graph of this lamplighter group. Okay. So it is not hard to see that if you look at the well, let's denote by Pn lamp the probability to return to the identity after n steps. When you do a random walk on the scalar graph of the lamplighter group. So the connection of this to the Anderson model is that if you look at our Anderson operator, raise it to the power n, and take the 0, 0 matrix element, the matrix element corresponding to the origin, for example, and then average over the randomness, then you exactly get this lamplighter return probability. So this connects. This is a well-known fact, I believe, and it allows to connect. The left-hand side is exactly the moment of our density of integrated density of states. The right-hand side is the lamplighter return probability. So this allows to connect the Lifshitz tails to return probabilities on the lamplighter group, and it turns out that the quantum Lifshitz tail for the Anderson model, which is this bound which I've stated above, is equivalent to two-sided probability bound on this P2n, which is exactly of the same form. So I believe this is at least some people knew it ages ago. At least I mean, I've learned it from people that knew it long before they explained it to me, and it's really folklore. However, as well as I mentioned, this left-hand side was proved by Barry Simon in '83, whereas this bound, the earliest reference which I found is Pite and Salofkost in '03, and they do not. Apparently, they didn't know at the time that it's equivalent to a well-known fact. But it's okay. In any case, both sides are well known, and indeed what we do is if it has some connection to their work. So I mean, this may look a bit ad hoc, but actually the right way to think about it is that our operator, it's not just an equality of moments. If you take the operator HV, the random operator, and integrate it in the sense of direct integral, over the distribution of the randomness. So is it clear what this expression says? I have a random operator. It depends on the randomness, so I can integrate. I can take the direct integral. It will act. This thing will act on the space L2 of ZD times the probability space. So if I do this, then I literally get the Markov operator of the Lamplighter group. Or in other words, if you prefer, you take the Lamplighter Markov operator. Well, this group is clearly solvable. So representation theory is very easy. You decompose, so you can do spectral theory based on the irreducible representations of this group. You decompose your operator into the irreducible representations. The irreducible representations more or less correspond to the realizations of the potential, and what you get in each slice is your the realization of your Anderson operator. Okay. In other words, we have the following commutative diagram. Well, we have this group, this Rath product of C2 and ZD, corresponding to which we have the Markov transition operator on the Cayley graph. And if we decompose it into irreducible representations, we get to the realizations of the Anderson model. Similarly, if we start with the 15 group, the group of the 15 puzzle, which is the semi-direct product of the symmetric group acting on ZD and ZD, to it we can associate the Markov transition operator which I've defined in the beginning, the generator of the random walk which we are studying. And now, since and this is what relates to this is the reason why I've decided to speak about this here. We are doing what all of you know much better than me, is that there is very natural to look at the decomposition of the regular representation into irreducible representations, and you have the natural probability measure, which is the Plancherel measure. In infinite for the infinite symmetric group, all this is less clear, since the left regular representation is believed to be irreducible, at least in most of the natural senses. However, there is one sense in which it can be decomposed. I'll comment on this later. If you don't believe me, you can think of finite volume at the time. And if you do this decomposition, the slices, you get a random operator, which is the creature which I would like to advertise, and I claim, based on this picture, that it should have similar. It should be somewhat similar, somewhat analogous to the Anderson model. And then the theorem, the similarity between our theorem and the quantum Lifshitz tails is supposed to motivate the analogy between the left hand side and the right hand side. Any questions so far? Is everyone lost already? I saw that the number of video participants decreased by a significant factor. Does this mean that I scared everyone already?
No.
No, not yet. So, any questions or? So, to make, in the case I scared you, let me make a digression into things which I think which are I think well known. So let me make a digression into the connection between representations of Sn random matrices, which I think it's a connection which has many faces. It's probably the earliest reference is the paper of Lifshitz from '74. And then this connection somehow was developed in many different directions. The route which I would like to pursue now goes through the works of Lifshitz and Kerov, and then of Kerov, which somehow had an idea which I find very beautiful and important, and then of Jan, and literally what I'll tell you now I've learned from Alexei Bufetov. I don't think this form appears anywhere in the published literature. So we do the following. We use the following construction. Let's consider the following matrix, which I'll denote H of Kn. Kn stands for the complete graph with n vertices. It's an n by n matrix, which is made out of transpositions. The ij entry is the transposition exchanging I and j in the symmetric group of order n. So it's a huge block matrix, where the blocks are transpositions. It acts on the nth power of the group algebra by left, well, in the nature of each block acts by left multiplication, and then the matrix acts as the matrices that we study in linear algebra. Is this okay? So. What we do now, we all know that the group algebra is decomposed into the sum of irreducible representations corresponding to Young tableau, where each representation appears as many times as its dimension, and accordingly we can raise all this to the power n. So if we the way I think about it, we have the Plancherel measure, which tells us which relative dimension does the representation lambda occupy in the left regular representation, and now we get we take h of Kn and make it act on lambda, meaning that is on e lambda to the n. We get what is random here. What is random here is h is not random. H is this matrix, but lambda is randomly chosen according to the Plancherel measure, and so this thing should be thought of as a representation theoretic analog of a random matrix. Let me try to explain in which sense. So, so it's an easy fact that this thing, this random matrix obeys the semicircle law. Easy both on average and in distribution. Easy as n goes to infinity, the eigenvalue distribution converges to the semicircle. Easy means that even though this is very simple representation theory, you don't need to know even this in order to prove it. If you know Wigner's proof of the usual semicircle law, which goes by by computing moments, you can do literally the same thing here. You compute moments check which paths give you the identity permutation, and then very fast you will be able to very quickly you'll be able to mimic Wigner's proof, and you'll prove the semicircle, at least in the mean, and also not with epsilon more effort also in distribution. So this is really an easy exercise.
Sasha,
Easy in
I have a question. Just the notation, so H, Kn, so and then bar lambda. What does that mean exactly?
So I take this H of Kn as a complete graph. I'm sorry for making this notation heavy, but the reason is to connect it to the previous story, which I'll do in a second. So this is H of Kn. This is one symbol for now. It's a notation for this matrix. Now I pick
just transpositions.
Yes. So now I pick a random representation lambda according to the Plancherel measure, and I act with this matrix on the nth power of this representation, on vectors with on n long vectors with components in this representation. On one of these. Okay. So it's well, the very natural thing to do. All of these are invariant subspaces, so it's the weight, the natural weight is the Plancherel weight, which exactly tells us what is the relative dimension of the group algebra, which each representation occupies. Okay. So that's what we do, and then you have the semicircle law, for which you don't need to know neither how the representations work, or in fact anything about the actual structure of the actual representation theory of the symmetric group. You just compute moments, and you're done. Okay. So this is not a very hard fact, but then there is another fact. Fact 2, which is I can't say that it's hard, but I find it non-trivial and very beautiful, and I think it's right to attribute it to Kirov, since it's a combination of two very nice ideas due to Kirov. One is a new way to write the Hooke formula, and another is the use of a piece of theory developed by Markov in the 19th century for the purpose of studying the so-called Markov moment problem. And this fact says that fact number 1, this one, is equivalent, literally mathematically equivalent, to the LSVK shape for the shape of the random Young diagram distributed according to the Plancherel measure. So as you probably know, but I'm not going to write any formula, but as you know, if you take a random Young diagram distributed according to the Plancherel measure, and you rotate it under scale, and you have a limited shape, which describes the diagram itself. And somehow it turns out that this fact is equivalent to the distribution of the eigenvalues of the action of our transposition matrix to this diagram. This is not a triviality. It's not hard. One can explain a proof in half an hour, I know, but it's I think it's nice and beautiful. Okay, so this is the end of the digression, and so the returning back to our story. So we have this operator h of kn, which is we can restrict it to a random representation. This is somehow an analog of a random matrix. Now in the same way, we can look at the operator h of zd, which is defined in exactly the same way. It's a block matrix acting on L2 of ZD to L2 of the symmetric group of the D. It looks scary, but I mean, I'm going to write down exactly the same thing as exactly the same transposition matrix, with the only difference that most of the elements are 0. I will only keep the elements ij when I and j label adjacent vertices on the lattice. So this is a block matrix with rows and columns labeled by the d-dimensional lattice, and the xy block is equal to the transposition exchange in x and y if x is adjacent to y and 0 otherwise. Perhaps you should divide by 2d. And then my the speculation is that if we take this creature, it's still a block matrix of convolution operators, so it's still we can still ask it to act on representations. My claim is that when we act with it on a random representation, again, I owe you an answer of what this random representation is. What we get is a counterpart of the Anderson model. And again, so maybe now is the time to say what this lambda is, since probably you have objections. We know, all of us know, that the left regular representation is irreducible. So the notion of random representation that we need here is comes from the recent work of Verchik and Tsilevich on the Fourier transform in the infinite symmetric group. If this gives us a notion of a random representation, it allows us, in the definition of the density of the integrated density of states, I've mentioned that well, there are two definitions for the Anderson model, this one and this one, and if we use the notion of random representation of Verchik and Tsilevich, then both of these facts extend to our setting. So if we do this, then the random measure which we studied, then the density of states which we study is indeed the expectation of mu0, where the expectation is over the choice of lambda. Okay. So this is the speculative picture which I would like to advertise. This is the end of the first and speculative part of my talk. If no one objects, I will make a break and then tell you something about something more solid about the actual arguments which enter the proof. And this will be basically independent of the first part, because. Yeah, so all this was my attempt to motivate the construction. Any questions?
It's perhaps a trivial question, but is there a line in between for random band matrices?
You're welcome to do it. I don't. I'm not going to be the person to object. To cutting out a piece and setting all the rest to 0. The question is, I mean, eventually this analogy should be tested by some less trivial features than the density of states. For example, Anderson localization. Now the problem is that you immediately, if you try to, in dimension 1, this model makes no sense. You can try to do a strip, but you immediately run into, it's somehow reminiscent of the hardest known case of Anderson localization with Bernoulli potential, because all the randomness here is discrete. So you should expect all the difficulties which you have in Bernoulli-Anderson, plus additional difficulties which have to do with the fact that you need to use some representation theory, which at least I haven't been able to do properly so far. So the representation theory is supposed, or even a kind of transparent proof of what we proved so far, would be to take our block matrix and act. Let's do finite volume. You don't need to. Then these are usually reducible representations of Sn. You take this block matrix and you act on it. Act with it on a Planck-Schreier random representation. What is the let's say, what is the largest eigenvalue that you get? For this matrix, the miracle comes from the fact that it has to do with the commutative subalgebra and Euclid's Murphy elements, which have a nice algebraic structure. For our matrix, there's no. I'll eat my head if there is a commutative subalgebra containing all these elements. I think they just cannot be true. So some new, some other methods have to be developed, and this is what makes this question fascinating for me. I probably answered more, told more than you other. Yeah, it's probably too long of an answer, but yeah, this is the. Any other questions? So what's the protocol? Do we make a break, and how long?
Yeah, so we could take a 5-minute break now, and then we'll resume at 3:55 Eastern.